In this work, we present learning certified control using contraction metric. We consider the problem of finding a tracking controller for a control-affine system. The dynamics of the system is known and described by a state equation. We want to find a feedback controller which is a function of the current state x, the nominal state x star, and the nominal control input u star. Controlled by this feedback controller, the actual trajectory of the closed-loop system is guaranteed to converge to any given reference x star. And also we want to derive some theoretical upper bound on the tracking error. We propose to learn such a controller using neural networks. For some reasons we will elaborate later, a metric function is also jointly learned with the controller. So what is a metric function? A metric function maps the state to a positive definite matrix. And as we will show later, the metric function provides guidance for the learning of the controller and also provides the theoretical upper bound on the tracking error. In order to get some guarantee on the tracking error, the metric function must be a control contraction metric. Now let us consider this system, and the dirt x is an infinitesimal displacement between two neighboring trajectories of the system. And the dynamics of dirt x is described by this differential equation. We see that a metric function m is a valid CCM if there exists a controller U such that this inequality holds. Clearly, this inequality implies that the norm of dirt x under metric n converges to zero exponentially at real lambda. Such a closed-loop system is referred to be contracting, which implies good tracking performance. Plugging the dynamics of dirt x into this inequality gives us this matrix inequality, where k is the gradient of the tracking controller with respect to the current state x. Now we have a sufficient condition for the closed-loop system to be contracting. Next, we will show how to jointly learn the metric and controller. Here, both the metric and the controller are parameterized by neural networks, and then this condition is converted into this loss function. And in practice, we use empirical risk minimization to optimize this loss function. It is also worth mentioning that the training process is fully offline, which makes it different from reinforcement learning. In the training phase, we do not have to simulate the system to collect trajectories. Instead, we just need to sample some tuples independently from the state space. Moreover, there is still a gap between empirical risk minimization and the actual sufficient condition we need. And in the paper, we provide two methods that can formally verify the learned controller. The tracking error of the learned controller is bounded. Specifically, we have the following theorem. If the norm of the disturbance is bounded by epsilon, then the tracking error is bounded by these two terms, where the first term converges to zero as t goes to infinity, and the second term is bounded. We evaluated the proposed method on several benchmark systems. On each benchmark, our method gives higher convergence rate and lower tracking error. Furthermore, the learned controller is represented by a small neural network and can be executed in sub-milliseconds. With the guaranteed tracking error, this enables real-time safe motion planning and control. In particular, it works for the neural lander. In this drawing model, the ground effect is learned from data, so the dynamics of this model is very complex and represented by a neural network. This shows the possibility that the proposed method can handle black box systems with the help of learning-based system identification. Conclusion. In this paper, we jointly learn a controller and a metric. The learned controller can track any reference trajectories. The tracking error of the learned controller is guaranteed to be bounded. The learned controller can be executed in real time.